In this video, I think it's time for a Learning Outcome Mastery Diagnostic Self-Check related to the physics of stationary waves that we've been covering over the past couple of weeks. Specifically, this question will deal with the learning outcomes, identify nodes and antinodes on a stationary wave, and determine the wavelength of sound waves using stationary waves. We'll be thinking about the wavelength of sound waves, but really to get to the idea of frequency, as you can kind of maybe jump ahead and see it here in our answer choices. So this is a worked example that comes from ACE Physics Syllabus Code 9702, paper 11 from May-June 2011, question number 25. It reads, the basic principle of note production in a horn is to set up a stationary wave in an air column. And here we've got a nice figure here of a horn with labeled mouthpiece and bell. It says for the lowest note produced by a horn, a node is formed at the mouthpiece and the antinode is formed at the bell. The frequency of this note is 75 Hertz. What are the frequencies of the next two higher notes for this air column? Probably the best thing to do here is to sketch this all out. And this really is a good question to explore the physics of stationary waves here. So inside of this horn here, there's a column of air. Now I'm just going to kind of sketch out a stationary wave form over here, but keep in mind that what I'm sketching out here would be kind of like a stationary wave that we might be able to achieve in this mouthpiece, but a much higher frequency than the lowest or the next higher one. But I just kind of want to remind ourselves what is a stationary wave here. So we have the node at the mouthpiece, and so here keep in mind that all of these different notes are going to be different waveforms that are occupying a fixed length, right? Like this horn isn't changing its size to get these different notes. It's just the waveform inside of the column of air is going to look different. And so a standing wave is typically when a wave goes out. I'm going to try to end at an antinode over here, and then it comes back and interferes with the first wave, and we get a pattern that looks something like that. And so I try to just draw a bunch of loops here in a standing wave, but here we see an antinode sort of at the end there, and a bunch of nodes, these points that I'm putting a dot on right there. And then the antinodes would be sort of these places in between the nodes, those points of maximum displacement. So the lowest note, 75 Hertz, is just this much of the waveform. Okay, the lowest note is going to be if here we have, say, our mouthpiece, the wave gets to the bell, there's an antinode there, comes back, and so we're just really seeing this much of the standing wave. And that's just 1/4 of a waveform. So 1/4 of a wave is equal to this 75 Hertz that they told us. 1/4 of a wave is 75 Hertz. You can see here that we have 1/4 of a wave, half of a wave gets us to a node, 3/4 of a wave, we're back at another antinode, and then there's the full waveform right there. Right, so one wavelength, remember, kind of looks like that, and we can kind of think about that as the phase of the wave, 1/4 of phase, halfway, 3/4, one full cycle, 360 degrees, or 2 pi radians. So what's going to be the next highest note? Well, we have to make sure that our standing waveform has a node at the mouthpiece and an antinode at the bell, and so here we're going to be kind of looking at like that much of the wave there. You see how we can get to an antinode right here? So I'll try to sketch out here again. We have this sort of constant length between the mouthpiece and the bell. So we know we're going to end at an antinode, and we started a node over here. And so this one's going to sort of open up like this node. Then it's going to go down to a node and then open back up. So it's the same length as that one. And so here you see what we're doing is that we see a node here, it ends in an antinode, and there's another antinode there. We have to sort of squeeze the wave together, so make it occur more frequently in order to fit it inside that fixed length there. And so here now we see we don't even have a full wavelength yet, right? That full wave goes from this node to this node. We've got 1/4, 1/2, 3/4 of a wave. And there's different ways to sort of think about the calculation. I mean, a very simple way is just to say, well, if this is 75, we have 75, 150, 225. And our answer is D, and we move on. Because as we sit for, paper one, we might be on a time crunch, and we don't really need to worry about it beyond that. But since we're taking this question as a worked opportunity, worked example to work through the learning objectives, let's kind of finish it for completion's sake. The second highest note, again, it's going to have to end in an antinote, but here now we're going to have to fit that whole wave, and then it's going to open up one more time. So it still ends in an antinode. This one comes in like this. That's not the best looking wave, but you get the idea. There we see 5/4 of a wave, and you've probably noticed a pattern by now. So rather than just sort of counting out the frequencies with each sort of quarter of a wave, we could think about it as if 1/4 of a wave is 75 hertz, well then multiply both sides of that by 4, and we could see that one full wave would have a frequency of 300 hertz. And so we could just take 3/4 of that frequency and get 225. We could take 5/4 of 300 and solve it that way. Well, like I said, just sort of counting it out. Whatever makes the shortest work of a question like this, but make sure that you take the time to work with the ideas. Sketching it out definitely helps. And so we saw that here was sort of our first harmonic, that much of the stationary wave. The next harmonic, we had to go all the way to that antinode, and so sort of this much of the stationary wave. And then the final, the second higher note, would be 375. We'd have our 75, 150, 300, our full wavelength, and then another 75, right, that we already kind of knew each quarter of the wave was 75 hertz. So our final sort of 375 hertz would be that waveform that corresponds to this figure here, right? But it may be possible to achieve even higher notes than that, but remember, we'd be fitting more waves inside of that finite space, that constant distance L, the column of air inside of the horn. So the correct answer here, choice D.